welcome to the fourth episode of Einstein's Entanglement, a short video series based on the book Einstein's Entanglement, Bell Inequalities, Relativity in the Qubit, published in 2024 by Oxford University Press. I'm your host and co-author of the book, Professor Stuckey. In this episode, I'm going to show you how quantum information theorists answered Mermin's challenge from episode 2 to solve the greatest mystery in physics. Using information invariance and continuity from the information theoretic reconstruction of quantum mechanics, I will derive the joint probabilities for the Mermin device in a way that anyone who has taken introductory physics can understand. And I will not have to invoke spooky actions at a distance, or causes from the future, or conspiratorial causal control over measurement settings, or infinitely many realities, or anything ridiculous. All I will need to add to information invariance and continuity is exactly what Einstein added to the light postulate for special relativity, the relativity principle. As I pointed out in episode 3, Einstein solved the greatest mystery in physics of the late 1800s by abandoning constructive efforts in despair and turning to principal explanation. That is, he solved the mystery of length contraction by showing how it follows from the equally mysterious observer independence of the speed of light c, and then justifying the observer independence of c by showing how it must be true given that the relativity principle and Maxwell's equations of electromagnetism are true. Thus, his principal solution to the mystery of length contraction can be written: relativity principle justifies the observer independence of c, whence the Lorentz transformations giving length contraction. Given the enormous success of special relativity, Carlo Rovelli suggested we try a similar approach to quantum mechanics. Specifically, he suggested we view quantum mechanics as a theory about the information that can be obtained about reality from making quantum measurements, rather than a theory about what causes the outcomes of a quantum measurement. In such a principal approach, we're ultimately interested in discovering fundamental principles that dictate the Hilbert space formalism of quantum mechanics, rather than a causal interpretation of that formalism. The first such axiomatic reconstruction of quantum mechanics via information theoretic principles was produced in 2001 by Lucian Hardy. And many have been produced since, with the first fully rigorous complete reconstructions, according to Marcus Mueller, published in 2011. They can all show how the Hilbert space formalism of quantum mechanics follows from some empirically discovered fact. But I will focus on those that start with the quantum bit of information, or qubit, according to information invariance and continuity. To do this, I will use a property of electrons called spin, as introduced in episode 2. When you measure an electron's spin vertically, you always get up or down, nothing in between. Likewise, when you measure an electron's spin horizontally, you always get left or right, nothing in between. In fact, this distinct splitting occurs as you rotate the magnets in continuous fashion. That's the essence of information invariance and continuity. It's just an information theoretic way to describe qubit superposition. Now suppose you first measure an electron vertically, or in the z-hat direction, and find its spin is up. Then you measure its spin in some direction b-hat, making an angle theta with z-hat, as shown here. What do you expect to find? Well, since spin is a form of angular momentum, Newtonian mechanics says you will simply obtain the projection of +1 z-hat in the b-hat direction, or +1 cosine theta. But since we're measuring Planck's constant h when we do a Stern-Gerlach spin measurement, we can't obtain a fraction of h, or a fraction of +1 here. However, +1 and -1 outcomes can average to cosine theta, and that with the requirement that all probabilities must total to 100% gives us the spin 1/2 qubit probabilities of quantum mechanics. If you don't know trigonometry, don't worry. Just believe what I'm telling you mathematically and keep watching. You will still be able to appreciate the result conceptually. So, the relativity principle tells us that the qubit superposition described by information invariance and continuity must be true, and shows us that the weirdness of qubit superposition resides in this average-only projection. So how does this lead to the mystery of quantum entanglement per the Mermin device? To remind you, Alice is measuring her spin entangled particle in the a-hat direction, Bob is measuring his in the b-hat direction, and the angle between a-hat and b-hat is theta. Then, according to quantum mechanics, their +1 and -1 outcomes obey these joint probabilities. This is what Mermin called the elementary quantum mechanical reconciliation of cases A and B necessary to solve the mystery of quantum entanglement as depicted with the Mermin device. Mermin's challenge is to derive these for the general reader without invoking spooky actions at a distance, or causes from the future, or conspiratorial control of measurement settings. When Alice and Bob make their measurements in the same direction, A hat equals B hat in our previous picture, they always obtain the same result as necessary to conserve spin angular momentum. Half the time both are +1 and half the time both are -1. So in those trials when Bob happens to measure in a different direction, B hat doesn't equal A hat, Alice reasons exactly as with the single particle case. That is, the spin angular momentum of Bob's particle is the same ±1 A hat as her particle. So when he measures that ±1 A hat angular momentum in the B hat direction, he should get ± cosine theta. But just as with the single particle case, Bob cannot obtain a fractional value for a measurement of h. However, his results can average the required ± cosine theta. Thus, we have this average-only conservation of spin angular momentum for the spin-entangled pair of particles, just like we had average-only projection of spin angular momentum for the single particle case. But since there is no preferred reference frame, Bob can make the exact same claim about Alice's results relative to his measurement direction. And when you demand that all the probabilities add to 100%, you get exactly the joint probabilities required for the elementary quantum mechanical reconciliation of cases A and B for the Mermin device. So, we have derived the joint probabilities for the Mermin device for the general reader without invoking spooky actions at a distance, or causes from the future, or conspiratorial control over measurement settings. We also didn't violate agreement between observers or add infinitely many worlds. This is how quantum information theorists in the second quantum revolution have answered Mermin's challenge. Now let's compare this solution to the mystery of Einstein's entanglement with Einstein's solution to the mystery of length contraction from episode 3. Again, consider the following three events labeled with the x and t space and time coordinates of two different reference frames in motion relative to each other, with times exaggerated for effect. In one reference frame, you have three sisters all the same age, and Alice is one of them. In the other reference frame, you have two brothers, both the same age, and Bob is one of them. The sisters and the brothers agree on the data labeling these three events as related by the Lorentz transformations, with the exaggerated time differences. Since the brothers are the same age, events 1 and 2 are simultaneous for them, and it's obvious from their organization of the events that the sisters' meter sticks are short, since the sisters measure the distance between Sarah and Alice to be 1,250 kilometers, while the brothers measure it to be just 1,000 kilometers. But the sisters are all the same age, so they say event 2 happened 2.5 years before event 1. The event that happened at the same time as event 1 is event 3. So from their perspective, it's the brothers' meter sticks that are short, since the brothers measure the distance between them to be 1,000 kilometers, while the sisters measure it to be just 800 kilometers. So, what causal mechanism is shortening meter sticks per this relativity of simultaneity? None. Length contraction is not a dynamical effect. It's a kinematic fact that follows necessarily from the observer independence of C as required by the relativity principle with Maxwell's equations. Similarly, consider the following data obtained by Alice and Bob when making spin measurements on a pair of spin-entangled particles with theta equals 60 degrees. Alice and Bob agree that these data are correct. When Alice orders the data per her plus or minus 1 results, it shows clearly that Bob's data averages to plus or minus cosine theta, or 1/2, according to average-only conservation from her perspective. But when Bob orders the data per his plus or minus 1 results by switching rows 2 and 6, it shows clearly that it's Alice's data that averages to plus or minus 1/2 according to average-only conservation from his perspective. What superdeterministic, or non-local, or retrocausal mechanism is responsible for this average-only conservation? None. Quantum entanglement is not a dynamical effect. It's a kinematic fact that follows necessarily from the observer independence of h as required by the relativity principle with Planck's radiation law. And there it is. Quantum information theorists have rendered quantum mechanics a principal explanation based on the exact same compelling fundamental principle as Einstein's widely accepted principal theory of special relativity. And that means Einstein's own relativity principle solves the mystery of Einstein's entanglement in principal fashion. How ironic. In the next and last episode, I will speculate on what we might infer about the nature of reality given this principal solution to the mystery of Einstein's entanglement.